This week's topics focused on parity checkers and modular design problems, as well as static logic hazards. In the lab this week, we're going to be focusing on practicing the modular design problem concept. We used to do a lab based on static logic hazards using a software tool called B2Spice. And your SPICE software is a way to simulate circuit elements, in this case digital gates. And you can, in this software, set specific delays for each gate. Because if you remember, for static logic hazards, these are taking into consideration the real delays through a circuit from going from your input to output of an actual gate. And so you can simulate this in this software and see the glitches appear in the timing diagrams. Now, I actually did not find this lab all that instructive, because if you hand draw the timing diagrams as you did in your homework, you get the exact same thing that the simulator would give you. So it's just using a software tool to do what you did by hand, and I think the drawing it by hand was instructive enough, so I didn't go asking you guys to download the SPICE software. But just know that that type of software is out there if you ever need to simulate actual gate delays in the circuit. Okay, so we are going to be focusing on modular design problems in the lab this week. And what I think is really cool about this week's lab is that you get to reuse code from your previous lab. So just like for the ripple carry adder, we reused the half adder and full adder that we created. In this week's lab, we're going to be creating a comparator module that makes use of the 7-segment display. So you're going to be reusing codes from experiment 5 and experiment 6, so your comparator module and your BCD, the 7-segment module, and combining them in ways that are described in the lab. So if we open up the lab for this week, you'll see that the first lab is a comparator display module. Basically, what you want to do for both of these experiments, for experiment 9 and 10, is start by drawing a black box diagram that shows your overall inputs and outputs, and then draw your structural module diagram, which shows all of the inner components and how they're connected, and label it all just like we've been doing in the past quizzes and homework. So you're going to be drawing your structural model diagram that's going to include your BCD to segment module from experiment 6 and your comparator module from experiment 5, and showing how they connect. And then you might need to be adding some other code to get to implement the assignment as described. In experiment 10, you'll also be doing that as well. You'll draw your structural model, show how everything gets connected using your previous codes, and then implement it. So when you go ahead and implement it, what you want to do is create a new project, add your old code from the previous projects. Remember just to copy the VHD file into your experiment 9 project folder, and then add that file to the project. And then create another module, which will be your overall box, which will use the structural modeling approach like you did for the ripple carry adder. And you will then add those components and connect them up based on your diagram. Then you'll test it in iSim and test it on your board. So for this lab, I'd like you to do both experiments 9 and 10 in the write-up for the lab report. So you'll have the structural diagrams, the iSim waveforms, and description for doing both of them. You can combine them together. But I only need a demo for experiment 10. Okay, so with that, I wanted to show you one other thing about iSim. I've just pulled up a project I was working on for 233 just to illustrate some things you can do with the waveform window. So we already know about the zoom full, and then you can zoom in on different aspects of your design. You can also change the color of your design. So if you right click on a signal, you can go signal color and change it to some other color. This might help you differentiate between signals. The other thing you can do is you can right click and change the radix. So we can, instead of seeing all these 1s and 0s, it might be more useful to us if it was maybe in hex. That can maybe make it easier to see, or maybe you might want to use unsigned decimal. We're going to be getting to signed decimal later on, so You could do unsigned decimal. This is useful when you have lots and lots of bits in one bus. You might not want to be staring at a whole bunch of ones and zeros. The other thing you can do is add dividers. So if you again right click and say new divider, you might want to have a divider for your inputs, and I'll add another divider maybe for your outputs. Then you can move these up and down by clicking and dragging, so that maybe you might have first, put that above here. Oh, pull this below. Okay, so you might show your inputs followed by your outputs or something like that. This is just to make your diagrams a little more readable for you. You can add whatever dividers you want. You could also add more of these markers. So let's say you wanted to describe something in your text pertaining to this specific instance in time. Maybe you also want to describe another instance in time. So if you right click on the marker, you could say markers, add marker, and then look, we got a second marker. So then you could say in your text, oh, at the yellow point in the diagram we see this, at the white point in the diagram we see this. So this just sort of helps you annotate the waveform. Okay, have fun with your lab.